Good morning and welcome back to computational mechanics. So as we seen on Friday, we solved by hand a finite element method problem of an elastic material. And if you think back to last Monday, you should have seen a theoretical class where I solved this same problem by hand with an example. I will pull the example of last week again, just because we're going to see today a way to solve the system without using the partition method, but using an approach that is called the penalty method, that basically is more easy to code in MATLAB and many solvers use. And it has a very tiny approximation, but we'll see this in a minute. So let me just bring the laser pointer out. This was the problem we've seen last week on Monday, and we had this metal plate with a hole. I will not go through this again. Just look at the last theoretical lecture video. These are the elastic properties and let's say the load conditions, etc. What we did, well, we had first an idealization and discretization step. So we saw there were lines of symmetry, so our model could then be reduced to study just this single triangle here. And what we then did was, as we seen on Friday, we identify the global, so the nodal displacement in the global reference system. So here we see that at node C, we actually remove the slider and we highlight the reaction R. We do this because we actually want to determine this value, and this is what we did Monday last week. Now, after we do this, we can then build the system to be solved. So we have the global stiffness matrix, the nodal displacements is equal to the load displacement vector. Okay. Now, if you remember, there was a very important step to do. That was to build this connectivity matrix in order to set up our system as a function of the element stiffness matrix. In this case, we have just one finite element. So this is our connectivity. Just for you to remember, we put the degree of freedoms 1 to 6. This is always like that if we use CST elements, because we have 6 nodal displacement for a 3 angular finite element. And then we add a row for each finite element we have in our model. And then down here, we represent the global degree of freedom number in correspondence to the position of the local degree of freedom. So 1 is the x displacement of this point here that corresponds to this point here, that in the local coordinate system is number 5. So we write 1 under number 5. Let's go to 2. Where do we write 2? Well, 2 is this displacement in correspondence of this node. So it will be written under number 1. And finally, 3 will be, this is the correspondence, so 3 will be under 3 in this case. So in red, I just put everything that is in global, let's say, coordinate system. And if we then write K11 as the global one, K11 is K55 of the element, and so on. So K22 of the global is K11 of the element, and K33 of the global was K33 of the element, and K12, so K12 is K51 the element, and so on. So we did this on Friday, and we've seen this on last Monday as well. So this was an important step to basically write our global stiffness matrix in terms of the local element stiffness matrix. Now here we have just one finite element. If you have more, you will have adding terms in this system. Now, how do we obtain the local stiffness matrix components? We have two ways of doing this. On Friday, we've used this where we compute the coefficients that we need developing this expression. So we needed the shape function, etc. This is a pre-calculated stiffness matrix, which you can always do and use. And this is for constant strain triangle only. And so basically, if you want K1, one of the element, you compute this. But look back at the previous class where I also report the terms of B1, C1, etc. So independent on the approach you want to use, what we can then obtain is basically write our system using the element stiffness matrix values just calculated. And then we've seen in the previous lecture how we obtain the equivalent nodal loads. And in this case, the result was PTL over 2 and PTL over 2 for nodes 1 and 2 with a minus sign because there was basically a pressure applied on the left boundary. So look back at the figure if you want to look at this. And then there was the reaction for node 3. So I'm going quick here because this is all what we did last Monday. So once we have our system to solve, we can write our global stiffness matrix in terms of the element stiffness components. Then we had our nodal displacements, and U3 was actually 0. In fact, we had reported the reaction R. Now, as we will see at the end of this class, this stiffness matrix is not invertible. So it cannot be inverted. It's singular. And therefore, I cannot just write this is equal to the inverse of that times that, because you will not be able to invert this. That's why to solve the system, we do a partition method. So basically, we don't consider, since we already know U3 is equal to 0, this basically crosses out these terms, and therefore we just use these equations here, this system, to solve for U1 and U2, okay? And these are the results that we got last week. And from these results, we can then plug them in here and finally solve the last equation to obtain the reaction. And this was the result. Now, it is possible to code such an approach also in MATLAB and finite element programs. The thing is that it's longer, more complicated, and perhaps less efficient. In particular, if you have many constraints and they're not well ordered, etc. So one very common approach to use to impose boundary condition is what is called the penalty method. This basically, it's a way to solve this system numerically and not explicitly as we just did here. And basically by adding very large terms in the stiffness matrix in correspondence of the element where the boundary condition is imposed, okay? So basically, how does this work? Well, if we had our stiffness matrix as this one here, but we knew that U3 is where our boundary condition is imposed and is actually a fixed boundary, so U3 is 0. How does this work? You add this penalty to the stiffness matrix, so a very, very, very big number with respect to the ones making up the matrix. And by doing so, you need also to to change the right-hand side, so the equivalent nodal load vector, in such a way that if we look at just the last equation, so basically let's look at the last system. So this basically means k13 times u1 plus k23 times u2 plus k33 plus 10 to the 20 u3 is equal to u3 bar times k33 plus 10 to the 20. Now u3 bar is actually the known, what we already know that we're going to impose, and we just leave u3 as an unknown. Okay, so if you look at this last equation that I've just spelled out, this is what you see. Now if this is very, very large, this means that these are very small, and if these are small terms, then we can write that basically only this term is almost equal to this other term. Okay, because basically we can, I mean, these are small with respect to the rest, so we can not consider them. And by doing so, then we can immediately see that u3, which we didn't know for this system, is actually equal or almost equal to u3 that we are imposing. Now, in this case, u3 that we imposed was 0, so u3 is 0. But u3 could actually be prescribed settlement, prescribed displacement, etc. So if you want to impose a prescribed displacement which has a non-zero value, this would still work. Now, once we do this, then this stiffness matrix, okay, it's now called the penalized stiffness matrix, and the objective is that to obtain U. Now, the penalized stiffness matrix is invertible. So if we can invert the stiffness matrix, the penalized stiffness matrix, then we can obtain U as the inverse of the penalized stiffness matrix times the nodal load displaced equivalent nodal load vector. Okay. Now, given this, then we can retrieve. So once we have our solution, we can then retrieve the reaction R, which we didn't know, by basically applying our nodal unknowns, the displacements that now we just calculated, using the original non-penalized stiffness matrix. Okay. Now, what is this large number to use? So what is the penalty factor and how do we calculate it? Well, we can either calculate it as a big number, so 10 to the 10 times the norm of the trace of the stiffness matrix. So basically, we add the square of each term in the diagonal, and then we take the square root of this. Basically, is to make sure that alpha is always going to be something which is very big with respect to the contents of this stiffness matrix, because if we'd say alpha is equal 10 to the 10, but these terms k11 or k1n is 10 to the 15, then we're not adding anything which is big with respect to the stiffness matrix. So that's why we want to have in the penalty factor something related with the terms already existing in the stiffness matrix. And so either this or, for example, and in the example I will show in a minute, I use the trace, so basically the sum of all the terms inside of the diagonal, so the trace of k. So where do we add these penalty factors? As I said, we add the penalty factor in correspondence of, well, on the diagonal term in correspondence of the nodal displacement vector where we know we have imposed the boundary condition. So if in un we had imposed a value of un bar, then we add alpha in this term, and then the equivalent nodal loads will be modified. So the right hand side is modified as well as equivalent nodal loads that you would obtain as in the standard approach, plus and then we add a term here that is 1 times un. Okay. I think sorry, I should have multiplied un times alpha. So there's an alpha missing here. I will edit this in the slides I will provide you. So there is an alpha that multiplies all this. We'll see in the example. So this is how we do this for to solve the system in MATLAB, and we then obtain our penalized stiffness matrix, our nodal displacement, so our unknowns, and the penalized, let's say, right-hand side. So in this way, we can then invert K penalized and obtain U. And with U, we then go back and calculate the reactions. So what about if we have multiple constraints? So let's say we want to constrain U3 minus 2U5 is equal to 3. Okay, so we have a system and we're constraining it in this way. And at the same time, we say that U2 is equal to U3. So U2 minus U3 is 0. So in matrix form, these constraints can read in the following way. So basically, we have 0 times U1 plus 0 times U2 plus 1 times U3, so U3, minus 2 times U5 is equal to 3. This is the first. And then the second one would be U2 minus U3 is equal to 0. So 0, 1 times U2 minus 1 times U3 is equal to 0. Okay? And C1 and C2 are these constant values that we impose. So to impose these conditions in the system in a matrix form, then basically we define this V matrix that is the sum for I is equal to 1 to 2, where in this case we have two constraints to impose. So these two equations of Vi, where V is this vector here, transpose times Vi. In this way, Vi transpose times Vi gives us a matrix. So we can then basically add, to obtain the penalized stiffness matrix, we add alpha in the right position using this, but we'll see this in the next example. These equations perhaps look complicated just without numbers in them. And then to modify the right-hand side, we then basically what we do for each constraint, so we impose Vi that times the coefficient Ci to the right-hand side multiplied by alpha. Okay, so F penalized is equal to P, the equivalent nodal load vector, plus A, that is this vector here, times alpha. So this is how you impose multiple constraints. And so in this class, basically, I've showed you the theory behind the penalty method. So you have to add a large term in the diagonal where the boundary condition is. You apply the penalty so that the equivalent nodal force vector is modified. Okay. Then you can solve the system inverting the penalized system stiffness matrix, and then use the solution, so the nodal displacements with the original stiffness to calculate the reactions. Okay, so I will now show you how in MATLAB how we can basically obtain the same result for last week. So this was the system that we solved. This is the solution. So U1 was minus 4PL over E, and U2 was minus 2PL over E, and the reaction was PLT. Okay, where L is, and this is the problem to solve. So I have a MATLAB here that I'm going to go and over, that basically is solving the same problem usually using the penalty method. Okay, so well, these scripts are provided if you look at the folder on Blackboard. So well, I first close all and I clear the memory and I clear the workspace. Okay, and then let's give some model dimensions and parameters. So just to have numbers so we can compare the theoretical solution up here with what we do in MATLAB. So we give it a thickness T of 1 millimeter, a Young modulus E of 30,000 newtons per over millimeter squared, a pressure P of 10 newtons over millimeter squared, and the length of this triangle here, 10 millimeters. Okay. I will also define the core and connectivity matrix or vectors. Well, they should be matrices, but here we just have one element. So it's just a vector, the connectivity. Just because we will then modify also the plot my mesh function in order to display also the displacement and the deformed mesh. Okay, so the core matrix basically was telling us for node 1, okay, it's x and y position. So node 1 is the top node, so it's node B in the figure above. Node 2 was node A in the figure just here, and node 3 was point C in the figure above. Okay, this is just because we had numbered in this way the global degree of freedom last week, and I'm just using the same numbering system. So the connectivity, basically we have one element that connects nodes 1, 2, and 3. So the system to solve, I wrote this here again. Basically is the same equation that you see up there. So TE times, well, this is sort of a way I try to write a matrix, but basically I report the same values of the stiffness matrix up here, multiplied by U1, U2, and U3 is equal to, well, here I already put the values, minus 50, and then the reaction. This is because if I put a breakpoint here and I run, I see that, well, U1 solution was minus 4 PL over E and gives us this in millimeters, U2 that, and then the reaction was 100, and the PTL over 2. So if you multiply P times T, so 10 times 1 times L, PTL, sorry. So the reaction was PTL over 2. So if you do 10 times 10, 100 times T1, 100 over 2 is minus 50 because we had a minus. So these terms were given. And so this was the solution from last week using the partition method. Okay. Now, well, I also, if I do display, then I write U1 is equal to this in millimeters, U2 is equal to that in millimeters, and the reaction was 100 newtons. Okay. Now let's code the penalty method and see if it works and how it works. So I will write down the stiffness matrix. So I will introduce the numbers above, and this is what you get. So the stiffness matrix is over here, and then we write the vector v that I was using to impose the boundary conditions. So where are we imposing the constraints? It was on node 3. So basically the v vector is saying that this times this, So 0 times u1 plus 0 times u2 times plus 1 times u3. So u3 is equal to 0. So v is this vector here. And then capital V that we've seen in the previous slide, if you go back and you have this notes printed, you can look at this, basically is a matrix that basically puts a number 1 exactly where we're going to impose our penalty factor in the stiffness matrix. And then C was basically what we're imposing, so this value here. And in this case, the displacement of node 3 was 0, so we put a 0 there. Now, the penalty factor is our large number, so I just put 1 to the 10 trace of the stiffness matrix, okay? So this is our alpha, and so the penalized stiffness matrix is the stiffness matrix plus this V times alpha. So basically, we're adding the big number in the bottom right corner of our stiffness matrix. So if I do a step, then we see that the penalized stiffness matrix has a very big number in the bottom right corner. Then the equivalent node load vector, we see it above there printed, but will look like this. So we have -50, and 0. This is the loads due to the equivalent nodal load vector. So in point C here, we don't have any pressure or load applied. We just have the reaction. But this is the equivalent nodal external load vector. Okay, so basically the penalized right-hand side is then P plus V transposed, okay, times C, which is the value 0 multiplied by alpha, okay? So this is the penalized right-hand side. So we want to solve our system. So we said our U is equal to the inverse of the penalized stiffness matrix times the penalized right-hand side. If we do that, we get our solution. And let's see what our solution tells us. The penalized U1 is minus 0.0133, which you see is exactly equal to the one that we got with the other partition method. U2 is equal to, well, it's the same. And finally, U3 is minus 2 times 10 to the minus 13, so is a numerical 0, okay? So set this, then we want to retrieve our reaction. So what will our reactions be? Basically, we calculate K, so the original stiffness matrix, times our solution, so our nodal displacement that we just obtained, and we obtain our P. And then we can then display our reaction as P reaction, okay, minus P3. This is the equivalent nodal loads. If we had, for example, a load applied on point C there, an external load, like, I don't know, a pressure was applied, then we had to remove that to the reaction, okay? So this is basically the penalty method to solve the system, which we'll use in the code that we will develop. Now let's plot our deformed mesh. So I just modified the plot my mesh function that we've seen in class to display basically our mesh and our deformed mesh. So I define a deformed matrix, well, array. In this case, first of all, I choose a scaling factor, because if I don't scale the displacement, this will be, unless we have very big loads, not visible in our drawing. So I just put a scale. You can play with this. You can make it smaller or larger. And then we see that we first define the deformation, okay, as basically giving this the coordinate of our nodes. But then basically what I do is that I add the displacement, okay, to the original coordinates, okay. So for example, for node 1, that was our node in B, basically there was a displacement in X. Okay, so the position of node 1 in the X direction is changed due to the displacement. And then the position of node 2, so point A in the X has been changed by the displacement, and the position of node 3 in X has been changed. Well, the solution tells us that the displacement of point C in X is 0, so the deformed should be as the initial one, and in fact this term is 0. So I basically find the position of the deformed nodes, so of the nodes in the deformed mesh, and I then will run this function. Okay, so I will show you the result first. So if I just continue, let me just sorry, this is not the okay. So in theory, you should see a figure. Let me just rerun this again without breakpoints. Continue. Okay, I don't know why. Let me just get the figure here. What is? Okay, I will add. Sorry, I don't know why this one is not working. Okay, so here is the figure. Let me just move it here. So this is the solution that we get. So we had our initial CST. There was a pressure here on the left, and these are where the nodes have moved. So U1 and U2, okay, are different. That's why I've represented this. Now let's just get in this plot my deformed mesh, which basically has the same structure of what we've seen so far, but basically I've changed the input. I still use the coordinates, I still use the connectivity, but then I give as an input also the deformed nodal coordinates, as we just calculated in the previous, well, just here. Okay, and so what I do is basically I create a figure where, as we've done before, we find the x and y position of our triangle, okay, of initial coordinates, and then we also define another triangle that basically has the coordinates of the deformed position, and then basically I fill in cyan, that is this light blue color, and then I also fill in blue, but then I use this phase alpha basically is to have it a bit transparent, and then I plot also the nodes of the deformed mesh, and so basically that's it. Basically it's still a loop through the connectivity. So in this case, for I is equal to 1, and if you look back, we used to use length here. It's better to use size, because length, in this case connectivity, is a 3 by 1. Okay, sorry, it's a 1 by 3. But if you use length, it will give you I from 1 to 3, because length just gets the longer dimension of the matrix. So it's better to use size, because we know that we want to know how many elements are here, not the size in general, the length of this connectivity matrix. Okay, so yeah, let's see if I change the scaling. If I put scale 1, this would be the real deform mesh. I save, I run, and I would obtain basically this the deform mesh. We can't really see, so you can play with the scaling. 200 will be even more, and this is what you get. Okay, so with this I will close today's class and see you on Friday, where we will solve another hand calculation, perhaps using the pre-calculated stiffness matrix, and I will set the second coursework where you will solve by hand, maybe, well, not maybe, for sure, a finite element, well, a mechanical problem with the finite element method, maybe with more than one element, 2 or 3, let's say. With this, I finish. See you on Friday.